Light is the fastest thing in the universe. It travels 186,000 miles every single second. But there is one star so impossibly massive that light takes 9 hours just to circle it once. How is that even physically possible? This is Stephenson 2-18, a red hypergiant sitting 20,000 light-years away in our own galaxy. It's the largest star we have ever identified, and understanding its size requires us to break down exactly what makes a star this extreme even possible. To feel the scale, let's start with our sun. Our sun is already enormous. Light takes about 8 minutes to travel from its surface to Earth. It could circle our entire sun in under a minute. Now imagine replacing our sun with Stephenson 2-18. Its surface wouldn't stop at the sun's edge. It would engulf Mercury, then Venus, then Earth, our entire planet gone deep inside the star, then Mars, and it would keep going out towards Saturn's orbit. Everything we think of as the inner solar system, every world close enough to feel warm, would simply be inside this one star. You could fit our sun inside it billions of times over. This isn't gravity doing this. This is a single star, just made almost impossibly large. Now here's the number that makes this real. Light is the fastest thing in existence. To travel just once around Stephenson 2-18, light would need something like 9 hours. 9 hours for the fastest thing in the universe to go around a single star one time. That's not a distance your body will ever understand, but your gut can feel it. This is a scale that shouldn't be able to exist as one object, and yet there it is. Why does a star like this push against the limits of physics? A star is a constant war between two forces, gravity pulling everything inward and energy from the core pushing everything outward. Make a star big enough, and that outward push becomes so violent the star can't hold its own layers. It starts blasting them into space. Stephenson 2-18 is right at that ceiling, shedding itself, struggling to stay together. A red hypergiant like this is in the last chapter of its life. It has burned through most of its fuel, swelled to this monstrous size, and it cannot stay this way. Sometime, on a cosmic scale it could be soon, the core will run out, gravity will win all at once, and the star will collapse and detonate as a supernova. When it goes, it will briefly outshine entire galaxies. It will leave behind either a neutron star or a black hole. The largest star we've ever found is not going to fade away quietly. It's going to end in one of the most violent events the universe is capable of. Violent events the universe is capable of. So hold both of these at once. Out there, right now, is a single star so vast that our sun next to it is a grain of sand. A star that would swallow the inner solar system whole. Light needs most of a day just to circle it, and it's dying, living on borrowed time, shedding itself into space, waiting for the collapse. The biggest thing of its kind we've ever seen is also one of the most temporary. That's the deal the universe offers everything, from the smallest life to the largest star. Get big, burn bright, and you don't get to stay. But before the collapse comes the shedding. Before the end comes the unraveling. The hypergiant's core is running out of fuel. Hydrogen has fused into helium. Helium has fused into heavier elements. Layer by layer, the star has exhausted its nuclear options. Soon, there will be nothing left to burn. When the core runs out, gravity wins all at once. The outward pressure that has held the star up for millions of years suddenly vanishes. The entire stellar mass collapses inward at nearly the speed of light. The rebounding shock wave races outward through the star's layers, heating them to billions of degrees. Fusion ignites one final time, a thermonuclear explosion of unimaginable power. The star detonates. For a brief moment, just seconds, the supernova outshines entire galaxies. The explosion is so luminous that it would be visible from Earth even if it were millions of light years away. But the light fades quickly. What remains at the star's core depends on the explosion's violence. If the core was massive enough, gravity wins the final battle. The remnant collapses further into a black hole, a point of infinite density where not even light can escape. Or, if the core was slightly less massive, the collapse stops at a neutron star, matter so dense that a teaspoon would weigh as much as a mountain. Either way, the hypergiant is gone. What was once the largest star in the known universe is now either a black hole or a neutron star, invisible or nearly invisible. The hypergiant's outer layers continue to expand into space, eventually mixing with the interstellar medium. The heavy elements forged in the star's core, iron, nickel, silicon, all the building blocks of planets and life, are scattered across light years. Somewhere in that expanding cloud, the seeds of new stars and worlds are already forming. These heavy elements, iron, nickel, silicon, carbon, are the raw materials for everything that comes next. They scatter into the void, mixing with the surrounding gas clouds. And then, over millions of years, something remarkable happens. That debris begins to clump. Gravity pulls it together again. New stars form from the ashes of the old one. This is the cycle. Stars die. Their elements scatter. New stars ignite. And around those new stars, planets form. The iron from Stephenson 2-18's core might become the heart of a terrestrial world. The carbon might seed the chemistry of life. Every atom in your body, right now, came from a star that died before your sun was born. So here's the real scale we need to hold. Stephenson 2-18 is dying right now. Its death is already written. But that death isn't an ending, it's a beginning. The violence of its collapse will forge new elements. The shockwave will trigger star formation across light years. Billions of years from now, planets around those new stars might host life that exists only because this hypergiant lived and died. This is why Stephenson 2-18 matters. It's not just a record holder. It's a reminder that even the most extreme things in the universe follow the same rules as everything else. It lives, it burns, it dies, and in dying, it seeds the cosmos with the possibility of new worlds. But here's what makes this particular star unique. Most hypergiants are hidden deep in star clusters, obscured by dust and distance. Stephenson 2-18 sits in a region we can actually study, and that means we can measure it, we can model it, we can predict what happens next with real precision. The models tell us something sobering. Stephenson 2-18 is unstable. Its surface isn't smooth, it's roiling, turbulent, shedding layers of gas into space, and those layers won't stay shed. Gravity will eventually pull them back, compressing them, heating them. And when that happens, the pressure at the core will spike. That spike will be the beginning of the end. The core temperature will rise past the point where the star can sustain fusion. Gravity will overcome the outward pressure, and in a fraction of a second, the entire star will collapse inward. The rebound will be catastrophic. When that rebound happens, the energy released will be almost incomprehensible. The star's outer layers will be blasted outward at speeds of 30,000 kilometers per second. The explosion will be so bright that, for a few weeks, it will outshine every other star in its galaxy combined. And then it will fade. What remains depends on the mass of the core. If it's massive enough, the collapse won't stop at neutron star density. It will keep going. Gravity will be so strong that not even light can escape. A black hole will form at the center of the nebula. The largest star we've ever found will become one of the universe's most extreme objects, and that's the final scale we need to hold. Right now, out there in the galaxy, Stephenson 2-18 is still burning. It's still shedding its layers. It's still massive beyond our ability to truly comprehend. But it's also temporary. Everything is temporary. Even the largest stars in the universe have an expiration date. And when they expire, they remake the cosmos. The question now becomes, how long does Stephenson 2-18 actually have left? Astronomers don't measure this in years or even centuries. A red hypergiant this massive burns through fuel at a staggering rate. The core is collapsing, the outer layers are being stripped away, and the clock is moving faster than we might expect. In cosmic terms, Stephenson 2-18 is in a sprint toward the finish line. While our sun will burn for billions of years more, a star this massive and this bloated is already running on fumes. The fusion reactions in its core are happening at a pace that seems almost frantic compared to stable stars. When that core finally collapses, it won't happen gradually. It will happen all at once. Gravity, which has been fighting against the outward pressure for millions of years, will suddenly win. And when it does, the rebound will be catastrophic. That rebound is the supernova. The core collapses so violently that it rebounds, sending a shockwave outward through the star at speeds of 30,000 kilometers per second. The entire star, all that incomprehensible mass, gets blown apart in a single, catastrophic explosion. In that single moment, Stephenson 2-18 will release more energy than our Sun will produce in its entire 10 billion-year lifetime. For a few seconds, it will outshine entire galaxies. And then, just as quickly, it will be gone. What remains after the explosion is one of two things. If the core is massive enough, and for a star this size, it almost certainly is, it collapses further into a black hole. If not, it becomes a neutron star, a city-sized ball of matter so dense that a teaspoon would weigh as much as a mountain. The most likely scenario is a black hole. And this black hole will be born from the most massive star we've ever observed. That means it will be a black hole of extraordinary proportions. It will have an event horizon, a point of no return that spans hundreds of kilometers across. And here's what makes this even more profound. That black hole will be orbited, for the rest of time, by the remnants of the supernova. Expanding shells of stellar material, glowing with the energy of the explosion, will drift through space for thousands of years. The death of Stephenson 2-18 will create a visible wound in the galaxy that persists long after the star is gone. But here's the thing that should really shift your perspective. Right now, at this very moment, we don't know if Stephenson 2-18 is still burning or if it has already exploded. The light we see from it has taken 20,000 years to reach us. That star could have gone supernova 19,000 years ago, and we would have no way of knowing until the light from the explosion arrives. So when you look up at the night sky, remember this. The light you're seeing from distant stars isn't showing you the present. It's showing you the past. And for Stephenson 2-18, the largest star we've ever found, that past might already include its own ending. The biggest thing we've ever seen might already be gone, and we're just waiting for the light to catch up. That light, carrying information from 20,000 years ago, is still traveling toward us. It will take another 20,000 years to arrive. By then, Stephenson 2-18 might already be gone. The star we're seeing right now may no longer exist. This is the nature of observing the universe. We are always looking backward. We are always chasing ghosts. And the larger the distance, the older the ghost becomes. For the largest star we know, we are seeing it as it was in the distant past. But here's what matters right now, in this moment. Somewhere in space, that star is still burning, still shedding its layers, still locked in the final struggle between gravity and its own violent core. The countdown is happening. We just can't see it yet. When a star reaches this stage, it stops being a stable object. It becomes a process. A slow-motion explosion that could end at any moment. The outer layers are already escaping, streaming off into space as stellar wind. The core is burning hotter, denser, more desperate. The physics here is brutal. Gravity wants to crush everything inward. Radiation pressure from the core wants to blow everything outward. For most of a star's life, these forces balance. But at this size, at this stage, the balance is breaking. And when that balance finally breaks, when gravity wins, the collapse will be catastrophic. The core will implode. The outer layers will rebound off the collapsing material, and the resulting explosion will be one of the most violent events in the universe. A supernova, maybe something even more extreme. For a brief moment, that single star will outshine entire galaxies. Billions of stars combined won't be as bright as Stephenson 2-18 in its final moment, and then it will fade. And what remains will be either a neutron star, a city-sized ball of neutron matter so dense that a teaspoon would weigh 1 billion tons, or a black hole. So this is the full arc. A star is born. It burns steadily for billions of years. It swells to an impossible size. It sheds itself into space. And then, in a moment, it ends violently. From creation to destruction, from the smallest grain of sand to the largest thing we've ever found, the universe follows the same rule for everything. Stephenson 2-18 is not special in this regard. It's just the most extreme version of the same story. The biggest, the brightest, the most violent, It burns hotter and faster than smaller stars,